Hello, AP Physics 1 students. We are going to go over the concepts questions we've already worked on, and in doing so I'm going to constantly going back to referring to the dog in the well analogy. So before we do, let's make sure we review it and make sure you know all the parts. So in your handwritten notes, I want you to write this down, all the parts of the dog in the well analogy, pause the video, and fill it in as to what each part represents. So the whole point of the dog in the well analogy is it represents really the beginning of the photoelectric effect experiment and later on the Bohr atom and the atomic spectra effects. So let's make sure we understand all the parts. So the dog, what does that represent? Well, that's the electron, right? The dog's the thing that's jumping up and down, the electron is the thing that's moving up and down. How about the well? Well, the dog is stuck in the well just like the electron is stuck in the atom. Hopefully you got that one. How about the rock? Well, remember, we throw the rock in to hit the lever to try to get the dog out, or to change between levels, the ledges there, and what's that analogy for? Well, that's going to be the photon, which is like a bundle of light energy. Here the photon is acting like a particle, just like the actual rock is a particle, a bundle of energy as a mass, is a bundle of energy as light. What about the depth of the well? Maybe you haven't thought of this before. And this is not exactly a one-to-one analogy, but the way I really want to think of the depth of the well is like the work function, right? So how far down the dog is, if it's in the, all the way at the bottom, you throw that rock in that just barely gets the dog at the top of the well, that represents the missing energy the dog had, and that's represented by the work function, the missing energy the electron has. You try to replace that with the photon, try to get it to just the edge of the atom. Now, what about the ledges of the well walls? This is a bit of a new addition to our analogy. Well, hopefully remember, that represents the energy levels, right? The dog could be on one ledge or the other, but the dog cannot float in between ledges. It's not a magical dog. Well, that was Bohr's idea. The electron can only be on one of these energy levels, these stable orbits, and it cannot exist anywhere in between. Okay, so now let's get into the concepts question. So here is an energy level diagram. It is not for hydrogen. This is for some hypothetical material who has a energy level diagram that's similar to hydrogen's, but it's just a little bit different. Alright, so we have the electron that starts in the ground state, so that's going to be all the way on the lowest part there, closest to the nucleus. That's just like a dog all the way at the bottom of the well. Letter A absorbs a photon, just barely get out of the atom. What's the energy of the photon? Well, of course, that's going to be 12 electron volts. You can see the electron is here missing 12 electron volts. You can consider the top of the well to be an energy of 0. That's like ground level. And if you can give it the missing 12 electron volts, then it would just barely get to the edge. What happens when bombarded with a photon with even more energy than that? Well, here's our equation. Ke max equals hf minus phi. Hf is the energy of the photon, and phi is the work function. So if you give it an energy hf that's larger than 12 electron volts, what happens? Well, it comes shooting up out of the atom, right, with extra kinetic energy. Just like we had done before, if I threw that rock in with 900 joules, the dog is missing 700 joules, it got to the top of the well with an extra 200 joules of kinetic energy, and that's what happens here. This is a successful photoelectric effect experiment, right? Alright, letter number 2 here. Electron starts at the ground state, given the following photon energies, which photons could absorb? Well, let's look at letter A here, which I've already boxed in as being a correct answer. If it started at -12 and absorbs 11 electron volts, well then it could jump up to this ledge here, and there is a ledge. There is an energy level there. Just like if you throw a rock in, giving the dog enough energy to get to this ledge, it can be there. It can get up to that ledge, and it's stable there, because it's a place for the dog to be. So here's a place where the electron can go, and it will go. So yes, this atom will absorb an 11 electron volt photon. Alright, so let's put it back to ground state. What about a 4 electron volt one? Well, if it's down here at -12 and absorbs 4, where would it jump up to? It would jump up to -8. But see, there's no level there. Just like the dog, if you gave it an energy to go here, well, there's no ledge there, so the dog can't just hang out there. The electron couldn't do it, so rather than the electron going up and coming back down like the dog would, it just wouldn't absorb it at all. So this photon, the 4 electron volts, would just pass this atom right by. It could not be absorbed because it would try to get the electron to a state where it couldn't exist. So the universe just won't let that happen. Alright, what about 12 electron volts? Will that work? Well, of course it will, right? Because it takes it right to the top. This is where you gave the dog just the right amount of energy to get it to the top of the well with nothing left over. It absolutely can absorb it. It will absorb it. Alright, how about the 5 electron volt one? Alright, so if it's here starts at -12 and give it 5 electron volts, it gets up to -7, and yeah, there's an energy level there, just like the dog, it would be stable there. So it will absolutely absorb a 5 electron volt photon. And what about 9? Well, if it starts at -12 and absorbs 9, then it gets up to -3, and there's no level there, just like there's no ledge for the dog, so this will not work. Okay. Number 3, electron starts in the second excited state. It absorbs a photon just barely get out of that, and what's the energy of that photon? Well, what's its energy? It's at -4, so how much does it need? It needs 4 electron volts to get to 0, right? The top of the well here, the edge of the atom is at 0 electron volts. It just needs an exactly amount to replace this missing energy. Now, what if instead it releases the photon, jump down to the first excited state? What's the energy? So here it's jumping down, Now here I think some students get confused. I know from experience some students don't exactly know how to use this idea that the change in energy electron equals HF. What I mean by that is that anytime the electron changes energies, it's got to be from one energy level to the other, and it does so by either absorbing or emitting a photon whose energy is HF. Now here it started at -4 and it went down to -7, and so it lost 3 electron volts. That's clear, except you can't say that the energy of the photon is -3 electron volts, because that would imply a negative frequency. So really the way I want you to think about this is by putting an absolute value bars around this, right? So whichever way the electron goes, whether it's gaining energy or losing energy, it's done by absorbing or emitting a photon of that difference in energy, the absolute value, the amount of energy. So when this electron loses 3 electron volts, that's because it's giving off a photon of 3 electron volts. So you can't have a negative here. That wouldn't make any sense. The photon can't have negative energy. All right, number 4. Electron starts in the 4th excited state. We want to list the energies of all different photons it could possibly emit. So the question is, from the 4th excited state, where could it go? Well, let's just go in order. It could jump down to the 3rd excited state. So it started at -1, and now it is -2. It clearly lost 1 electron volt, so it gives off a 1 electron volt photon. Again, thinking about the absolute value idea. It loses 1 electron volt. It loses it as a 1 electron volt photon. So that's one transition. Now from the 4th excited state, where else could it have gone? Well, it could have jumped down to the 2nd excited state. Here losing 3 electron volts, so we have a 3 electron volt photon. Or it could have gone down to the 1st excited state. So between -1 and -7, how much did it lose? It lost 6 electron volts, right? So it gives off a 6 electron volt photon. We're just going to draw all these transitions on here. Where else could it have gone? It could have gone all the way down, losing 11 electron volts. So it gives off an 11 electron volt photon. But that's not all. Because if it started here in the 4th excited state and jumped down to the 3rd excited state, well, from there, it could have jumped down to the 2nd excited state. So losing 2 electron volts, so it could also possibly give off a 2 electron volt photon, and that will appear in its emission spectrum. But from this level, where else could it have gone? It could have gone down to the 1st excited state, giving off from -2 down to -7, 5 electron volts. That's a possibility. Or it could have jumped all the way down here, losing 10 electron volts, so it can give off a 10 electron volt photon. All of these will appear in the emission spectrum. But wait, we're not done, because once it's in the 2nd excited state, tumbling down from here, where can it go? It can jump down to the 1st excited state. In doing so, it went from -4 to -7, giving off 3 electron volts, but we've already listed that one, so there's no reason to list it again. If you did, okay, but it's not necessary. However, from the 2nd excited state, where can it go? It can go all the way down to ground, giving off 8 electron volts from -4 down to -12, so it loses 8 electron volts, giving off an 8 electron volt photon. And there's only one more, because once somehow it gets down to the 1st excited state, from here, where could it go? Well, it's only jumping down, so it's going to jump down to the ground state, giving off 5 electron volts, but we've already listed 5 electron volts, so here's our entire list. 1, 2, 3, 4, 5, 6, 7, 8. There are going to be 8 possible photons, or 8 possible frequencies, I should say, in its emission spectrum, given the fact that it started in the 4th excited state. All right, number 5. Electron starts in the 3rd excited state. Can it absorb a photon with 7 electron volts of energy? Well, of course it can, just like before, right? It just has extra. Ke max equals HF minus phi. So, phi really here is -12 electron volts. I should say 12 electron volts, but now we're sort of like resetting the bar. So here it's missing 2 electron volts. If you give it 7, well, it has more than it needs. So it would come out with an extra 5 electron volts of kinetic energy. All right, number 6. If this element is involved in the photoelectric effect experiment, what's the cutoff wavelength? All right, so cutoff or threshold is the idea that you give it just the right amount, assuming it starts in the ground state, to just barely get out of that and with nothing left over. So we say that, Ke max is 0, and we're dealing with wavelengths, so we write this as h over lambda. So h over lambda, the energy of the photon just matches phi. So h over lambda equals phi, and you can go ahead and substitute the numbers here. What's phi? Just the depth of the well, right? It's the 12 electron volts. Make sure it's not negative, right? Negative 12 electron volts is indicating how much it's missing. Phi itself, remember, is a positive number. In this case, the electron starting in the ground state would be missing 12 electron volts. Which value should we be using here? Well, if we want everything in electron volts, we have to be using a value of h in electron volts. Or, hey, we got hc, so it's a great time to use the 1240 electron volt nanometer shortcut, considering we probably want the wavelength in nanometers anyway, like we almost always do. And you should have no problem getting 100 nanometers. Why am I saying 100? Well, because we have 2 sig figs in 12, right? Now, if you have an extra third sig fig, you write it as 103 nanometers, but that's not exactly right. So, all right. Letter B, is this the upper or lower limits on the wavelengths? If you didn't get this quite yet, pause the video, give it a think through, write down your answer, then see what I say. Okay, so it's all about where wavelength is in the equation. Wavelength is in the denominator. Remember, h over lambda is just another way of writing hf. This is the energy of the photon, and lambda is in the denominator. The idea is we want the energy of the photon to beat phi, right? And so if lambda gets too large, then the whole value of this gets too small, and that's the problem. That means that 100 nanometers is the upper limit. That's the largest lambda could be. It's the largest wavelength. Anything larger causes the energy of the photon to be smaller than phi, and now we don't have a successful photoelectric effect experiment anymore.